One of the reasons I did this talk is that in my current day-to-day, I have to deal with Kubernetes clusters, Linux machines, and in general, whatever happens in those clusters. So it's a bit difficult sometimes to understand things like we create SAS database. So one of the things we need to know is, for example, how many bytes have been written in that file today. And it turns out that it's not pretty straightforward to do these kind of things. So we started exploring a bit about how can you extract those information from the kernel. And it turned out that then at some point we discovered that there's this thing called eBPF. So myself, I didn't know about eBPF 1 year and a half ago, but I had this opportunity to explore a bit. And so I wrapped up this talk to tell everyone else about it. So eBPF stands for Extended BPF. BPF is basically a Unix feature that lets you get some information from the machine you're running on using a syscall. It historically stands for Berkeley packet filter, so it seems to everyone that it's about just networking, but it turns out that it's not actually, at least not in Linux machines, because it has been extended to do many more things. In this context, we are talking about BPF as a tracing framework. This is the use case that was focused on because I wanted to extract information from my machines, but it turns out that it can actually be used for other things. I will tell a bit more about the other things it can be used also so that you know about it, but it's not what I'm showing here. BPF is itself, it's not about extracting informations or doing things basically like instrumenting the kernel, but is something that you can use to instrument other frameworks that are already in the kernel, right? So, for example, the kernel has some tracing backends that you can use, static trace points, key probes, uprobes, where you see them. So you basically use the BPFs to access those tracing frameworks. BPF itself is not the tracing framework. It is the tool that you use to instrument the tracing framework to go to the kernel and use the tracing framework, right? Instead of going there with kernel module or with a syscall, you go there using the BPFs. One of those tracing frameworks that is posed by the kernel is the static trace points. Static trace points are basically trace points that are fixed in the kernel that are already there for you to use. They are defined, if everyone can see, there's this folder where you can see by basically printing a file where you can see all the static trace points defined in your machine. And those have been defined by the kernel developers, so they are already there. They have their arguments, their returns, and you can extract information from them. We'll see how after. What's very interesting for everyone on the other end is to be able to define dynamic tracing functionalities. So those can be in the kernel or in your user space programs, namely key probes and uprobes. So key probes is the backend that lets you extract information from the kernel, so you don't attach key probes on a binary, but you attach key probes on the kernel itself. So your key probe can be attached to a kernel function. For example, if you want to see, as the example I made before, how many bytes I've written for a file, you attach a VFS write. VFS write is the function that's basically called in the kernel every time a file is written. So everything in Linux is a file, so that's it. And VFS read. On the other end, with uprobes, you can attach your program's function. So we will see that in a program that I have. It's called catturday, show cats. That has a main in the main package. It's a Go program. It has a variable. It has a function that returns a variable that is an integer, that is the counter of the requests that this program received, and it is in user space, and you can attach to it by attaching a uprobe. And then there's XDP. This talk is not about XDP, but I want to tell everyone what this is. XDP is Express Data Path, and this framework built on top of eBPF to allow you to basically do packet mangling and manage your packets. So you can do like implement things like firewalls, but it allows you to do more than just like, reject the packets in kernel space. You can reject the packets directly in the network card so that you don't even populate the task struct, the socket buffer struct for the packet that gives you a great performance improvement because the kernel didn't even process the packet. So this eBPF thing is all about doing the processing of your information in of them in user space. There's a mechanism in BPF that's called maps. There are a wide set of maps that you can use that basically allows you to aggregate information at kernel level so that you don't overwhelm your user space. Because the kernel can easily deal with like thousands of packets, for example, that you want to analyze, but it's better to not send them, all of them in user space if you just want to know the bytes that the packet have been written in 10 seconds. You can do that in kernel space. The life cycle of an eBPF program is quite simple when you have seen it. Initially, it seems a bit crazy that you have this situation, but the idea is that you have a program that is written for a specific instruction set, that is the eBPF assembly, basically, instruction set that runs on the eBPF virtual machine. The eBPF virtual machine is implemented in a kernel, and it has a thing called static verifier that is a process in the kernel that basically ensures that you don't kernel panic this machine. So as opposed to like writing a kernel module that, of course, gives you like more opportunities in terms of customization of the kernel, an eBPF cannot kernel panic your machine, or in general doesn't allow you to do bad things. And this is both a nice thing, but also a bad thing, because sometimes you just want to do things, and it doesn't allow you. But it's nice that there's something looking at us. And then the eBPF syscall there. So basically, you have this eBPF bytecode that you can compile with, for example, Clang as a backend that's called BPF. So you Clang emit BPF, and you basically can write a C program that emits a BPF program, and then with the syscall BPF, you load the program. All these things seems crazy, but there are higher level of programs that lets you do things. And then by passing this argument to the BPF syscall, you load the program, the static verifier reads the program, ensure that everything is okay, and then the BPF syscall, the BPF VM, understand what kind of program this is, a key probe, a U probe, a static trace points, whatever. And if it's the case that the program registers itself to a map, that it's what lets you get information back in user space, is basically your communication medium to get out, like, for example, like, contract is a thing, right? You could implement contract with this thing, with the BPF. And to get back the information from contract for your own contract, you will have to use a map that gives you a stream of the connection that has been opened. And the mustache part there says that a BPF program are not Turing complete. So basically, you cannot do loops. So that's because of the static verifier doesn't allow you to do that. But if your loop is, for example, like like you have a list of server or a list of IPs for your network interface that you have to control, these kind of things. If it's a fixed loop that you have to do, like it has a set of elements you already know at compile time, you can now roll the loop with a pragma call in your compiler, for example. Or you can just write down 10 times the thing. And what about today? I mean, seeing that this thing is pretty crazy, some of you know this. I started doing this talk 1 year ago, and well, maybe it's because here is FOSDEM. So The people that come here are more like on the edge of these kind of things, especially for the Linux kernel. But in general, no one knows what are the applications today. One of the most common is TCP dump. Who uses here TCP dump or used it? Everyone, basically. Not you over there, but I see you. TCP dump is a program that lets you basically dumps out the packets that you're receiving in this machine or in a specific network interface you're pointing to. The TCP dump program that I'm using here basically gets all the IP packets and the IPv4 and TCP and on port 80, so this could be HTTP traffic. And if you pass the D parameter to TCP dump, it dumps out the BPF program that it's loading to do that. So TCP dump actually uses BPF program even if you didn't really see them. So BPF are a mainstream thing now. Even if maybe you are not yet like implementing them in your programs, they are a thing for everyone. And the things that dumps out here is the instruction set that it's the portion of the instruction set that this is using. And if you look at it, it's basically like a reflection of the RFC implementation, right? So these two instructions mean, is this an Ethernet IPv4 packet? I don't do this thing like automatically, so like if I will not have written this here, I will not know. But I did the math at home and wrote these things out. And is SRC X plus 14 on port 80, so 15 hexadecimal, and same thing for destination. So since I didn't specify here SRC 80 and destination 80, this is assuming that it's always 80, and it's basically adding two instructions, both for source and both for destination. Who uses Kubernetes, containers, Docker, whatever? Raise your hands. One of the main, basically, isolation technique that container runtime uses to basically allow you to share your kernel between your container and the host machine is seccomp. Seccomp, what does seccomp do? Basically, like if you go to the Docker repo, you will see, it's a Mobi actually repo now, you will see that it has a predefined seccomp set of rules that basically doesn't allow you to cap sysadmin, so you don't become network administrator, these kind of things. And it turns out that seccomp has an eBPF subsystem that you can use to define your own like rules, as compared to like, because seccomp lets you like just define rules, say block this syscall, block this syscall, block this syscall. But it turns out that with the BPF subsystem, you can actually write your own rules. If process ID is odd, block the syscall, right? These kind of things. Probably the use case I just told, it's probably a bit silly, but it's something you can do. And in this situation, I just compiled this program here. And the program I did is printing hey there, and then, it is installing a filter with this function I defined here. As you can see, I'm basically writing, using a DSL to write the BPF assembly here. You don't really need to do that. I didn't really know what I was doing. Yeah, it took to me so much to end up with that thing. But it turns out that like I could have written this in C and compiled with Clang and copied it here. And it's basically the process that I used. But I really want to be very cool and write there the assembly. So that's what I did. And then basically I load that BPF program in seccomp with those instructions. And this filter is installed in the NR write, so I'm blocking all the writes to everything, and on this architecture, and I give back an EPERM when you try to write. So everything I'm going to write after this second registration is going to be denied. So I just started that program I made with strace just to see. And the first call went OK, and all the others just gave a pair and exited the program. What are more practical examples? Trace file open by file name. I've written a bunch of them. Go runtime events for XDP firewalls and packet rewriting. Trace commands in a bash shell. Write a keylogger, whatever you want to write. One of the use cases I use a lot is, since I work for Influx, trace query done against a database. Like, I don't do the core of InfluxDB, so I don't really know where to. I don't really want to mangle with their code because the core engineers don't allow me. But I don't really want to do that. So I just load an eBPF program to see what's happening. Yes, it's crazy, and no one's ready to do all of that. This statement is probably to another conference and not at FOSDEM. So higher level APIs are not for FOSDEM people, but let's see them anyway. An interesting project is iVisor Go BPF. If you're a Go programmer, you might want to just load your BPF program using Go, actually. A Go BPF is basically a binding that lets you load BPF programs and compile them and load them. So you just provide the C program, as I did here, like a util read file, bash read line C. I will go to that program in a second. Or you can give Go BPF the program already compiled. The difference is that if you ask Go BPF to compile the program, in the target machine you will need to have the compiler, basically, while if you give the program already compiled, you just have a simple Go binary in the target machine. But the real innovation in this repo is that it allows you to register to the maps that I told you about before using Go channels. So you can actually read the maps in a concurrent way. Let's go very fast through this program. I just read this bash read line C here. What is this doing is that it's basically doing some verification that are required for the static verifier to let your program work. And then I get the current process ID. I register it in this event that I created here, that is coming from this struct, that is also registered in my Go program. So I have to maintain, when I send the data with the map, I have to maintain the struct both in the BPF program and in my Go program. And then I register this BPF perf output map. That BPF perf output is the map that you want to use when you want to have a generic map to send things. Like if you don't want to use a specific one, this one is generic and it's always registered and works very well for like debugging use cases. So BPF perf output here, and this is the same real-line events here and real-line events in this case here. So I register to this table, and every time the function read line is called on bash, I send an event. So this thing is basically, you start a bash shell everywhere in the machine, and every time read line is the function in bash that's called whenever command is issued. So when you write a command in bash, read line receives it, read line is a function, so you're getting the argument of the function, and you send it to the map, and the map is received in Go here, in this table, and then this table has a channel, and this is connected to the table, and then you just get the information out of the channel using the for loop here. And then you print them basically out. So if I load this program in a Linux machine, what happens is that I just see all the bash command issues. Another interesting project always in iVisor is BPF trace. BPF trace is an higher level language that has been written for the purpose of doing BPF tracing. And it's a bit easier because you don't have to deal with all of this. This is still very good because it's very extensible. Like you can write basically your own Go program and having it interact with the BPF program. But if you just need some specialized tool, like just extract all the writes, maybe you don't need like to do anything else with them. You just want to see them. It's easier to use BPF trace. I'm always talking about this IO Visor because it's the Linux Foundation BPF project. It's basically right now the main contributor to BPF. Other contributors that are very notable are me, I'm joking, and are Cilium, that is basically they are doing their SDN for Kubernetes, but they basically wrote the documentation for a BPF. Like if you write the BPF documentation in DuckDuckGo, whatever search engine you use, I will not, you basically find them. Well, that's what I found, actually. I didn't find anything, other documentation else. And other contributors are the guys at Kinvolk. We have one of them there. And all the others. I will tell them about that later. But IO Visor is the main contributor, actually. And Brendan Gregg, that is working on Netflix doing performance, created this graph here showing you all the interaction point with the BPF using BPF trace. So you can easily see that I was always talking about VFS. So if you're interested in the file system, you can go as down as you want, down to the device drivers. Same things for sockets, same things for the scheduler, for virtual memory. You can interact with the syscalls, you can interact with the system libraries, up to the applications. And you can connect to all of these things using the trace backend I said. Tracepoints, hardware, profile interval, kprobe, uprobe, USDT. USDT is very interesting. I didn't add those in the slides because I didn't want to make this all very long. But it's basically allow you to define static trace points in your programs. One of the most notable projects that uses this is Node.js. Node.js already has USDTs defined so that, for example, you can get all the arguments to node functions using USDTs because a node program it's not like compiled to an object. So how do I do these kind of things with an interpreted language? Using USDT. And what about Kubernetes? Yeah, finally. Turns out that there's not really anything for Kubernetes. There are a bunch of projects around, but not a lot of projects that are like in a group that actively maintains them in a way that they are used very broadly in the community. With my friend Leonardo there, we had an idea to use BPF trace against Kubernetes clusters, and we create this plugin called kubectl trace. Then Brendan Gregg noticed it, and we contributed that to IO Visor, basically. So now it's IO Visor kubectl trace. I will have a demo shortly. There's a little disclaimer. This is not my laptop. That's very funny. I left my laptop at home, so this is Leonardo's laptop. So if you see Leonardo around, it's not my fault, and if it doesn't work, it's Leonardo's fault. So yes, of course, you can all punch Leonardo in the face later. And so you can find kubectl trace in IO Visor. The philosophy behind BPF trace and kubectl trace is that they are Unix tools, following the Unix philosophy. So you just run them, see the results, and they're gone. It's not a kind of tool that you can use like to let your program run there forever, or that you can hook to other things. You just, hey, I want to see all the file written. Hey, I want to see all the connections. You see them, and they're gone. The usage is kubectl trace run BPF trace program, and then since we are in Kubernetes, your node or your pod. So you can attach a program to a pod specifically or to a node, and then you just attach a TTI with A. An interesting use case, it's seeing, for example, the distribution of read in a file. Like, you're reading a file, right? But you never know how you're reading it, right? It's a question that the first time I asked myself this question is, what do you mean with that, how I read it, right? I just read it, right? You don't just read a file. You can read it in different ways. You can read it in chunks of like 1 gigabyte or in chunk of 2 kilobytes, right? And that gives you different performances. So like if you're writing a database like we do, and you're reading or writing files a lot, this is a very huge difference. Like if you write cache to a file in chunk of 1 gigabyte or of 1 kilobyte. And this tool gives you an insight of that, BPF trace, and by extension, kubectl tracing clusters. And since with kubectl trace or BPF trace, you can define your own output format, you can like write CSV, and then you can pipe it. As I said, it follows the Unix philosophy. So you can pipe it to another program like Visidata that lets you plot your results in a different way than kubectl trace does. So BPF trace has functions to aggregate your results like histograms. You can see the maps as sums, these kind of things. But if you want to aggregate them yourself, you can do that in user space. And there's a demo time. Leo, you think it will work? Who knows? So I try to do my best to be comfortable with this machine. So I have this Kubernetes application called Caturday that shows cats. Seems fine. And basically, it's a deployment with 3 containers and runs this Caturday thing that has an HTTP server that shows you cats in the browser and cats in the terminal with a row endpoint. So just run it. And I see my cats. One of them are already running. And see that there's a service where I can reach cats, and it's over there. Then I have to use bash because the thing gets me crazy. And this Caturday program is implemented in this main Go file. And yes, it has cats. And what I'm interested in is getting out the value of this counter value. Counter value is called, we will see in the cats now, it's called every time someone calls endpoint that shows cats, if it's for the normal endpoint or for the row endpoint, so basically we see 1, 2, 3 times. It's an atomic counter showing how many times the cats are being showed up. And I just want to be able to extract that information without having like, well, you can monitor this like adding a Prometheus endpoint or adding an influx client and send information out, or log to a file and send them somewhere, or you can extract information using an eBPF. And that's what I want to do, so I have the cats here, I have a pod. And what I want to do is this one-liner here. So it's big enough. And I want to do kubectl trace run uretprobe. Uprobe doesn't give you the return value of the function. Uretprobe gives you the return value. Keyprobe and keyretprobe, same thing. So I attach this uretprobe to my I don't really know what the binary is in the container, so I just use its process ID and get the binary from exe. And I want to print the counter, and I will get the value from this main counter value. And the pod is this one. So where's the pod there? One of them, maybe this one. And I just use it here. I start this thing. When I have it started, I can do kubectl trace get. Oh, export. Or maybe it's better to start it here. Okay. I didn't have the environment variable for Kubernetes. And okay. It started and saying, hey, I'm waiting for you to send a Control-C because Control-C, that signal is used to tell the program to dump out the maps in BPF trace. And so I can do trace get. Oh my, not my keyboard. In an namespace. So the experience is very similar to the normal kubectl programs. And I say that I have this kubectl trace here, and I see that it's attached. Now, I just want to like do a curl to the cat endpoint that is in the network namespace. And okay, this is the HTML endpoint, and I just want the row endpoint. So you see that I have this counter with 3 cats here showing 4, 5, and I have this number here too. So every time I call the cat, it gives me the counter increasing from the BPF, extracted from my BPF trace program, started from my laptop, and the cluster might be anywhere. So it's a very good helper to extract information this way. And other one-liners I prepared for this are like this one. Same node. In this case, in a node, they want to see how many times the center wildcard syscall has been called. And I'm creating here a map called probe at, and parentheses is create a map. And the count function lets you see how many times this set has been called. And same thing. I will wait for it to run. Oh, I didn't do that here. Okay, cool. Touch. Attaching 300 probes because center syscall a lot. And then I just plot the results. So center socket 435 times in 1 second. Right? But another interesting one is counting BFS writes. So this is what I said before. Every time a file is written in the Linux kernel, it goes through the VFS. VFS write here, well, this is not C. I can import Linux headers in BPF trace using the same notation. I can create structs using the same notation so that it's easier for one to extract informations. But so I extracted the file information from the file descriptor, and then I create a map that has file name and the sum of bytes that have been written. this node, and they attach. And then I just go to the internet and do some things, just because it creates some, well, this Kubernetes cluster is running on this machine, and this machine is under control. So, and this is not my GitHub because it's Leonardo's GitHub. And I just Control-C here, and I see that there's some stuff running. I see that TCP v6, because the FOSDEM internet is in IPv6, so it's not TCP. And I see that Firefox is doing a lot of things with SQLite and everything. And another interesting thing is seeing the same thing with an histogram. So let's still go around, open Saturday, whatever, and Control-C. In this case, I'm seeing not just the file, the bytes written, but also the distribution of the bytes written per chunk. So like for this cookie SQLite 12, I see that it's between 16 and 32 bytes, or between 32 and 64 kilobytes. While if I go to TCP, it becomes extremely clear that the TCP RFC has been implemented correctly, because it ranges from 16 bytes to 8 kilobytes, right? So if you're implementing your own TCP, you can debug that with this. Who doesn't do that? And turns out the resources for eBPF are starting to pop out from the internet, but there's not really yet a book for it. So David Calavera and Jesse are writing one, and this book is coming out from a really sometimes this year or next year. I don't know. It's not yet public. It's not public yet, but the book is coming. And as I said, there have been contributions from iAdvisor, Cilium, and other entities. Linux security models use this eBPF thing, and there's a slide with references for you. So if you want to take a photo and check the references for yourself. And it's everything. I bought a nice domain. It's called BPFSH. Nice. If anyone wants an alias, just write me an email. I will be happy to give it to you. Just because this community wants to have more people looking at the BPF, and having a nice email put you in a situation so that you have to do that because you have the email address, right? I'm joking. And if there are any questions,
thank you for
it's shut down. You want to use mine?
low battery. I think I can do it with boards. Do you have any questions? You would have to speak up. I'm sorry. Unfortunately, the microphone is dead. You would have to repeat the question for the recording.
If I understand it.
So, my question is,
I don't hear it.
so, yeah.
You can call me if you want. I don't mind sharing my thing here.
The question is, if you're on control, is it possible to target?
I don't hear you.
Okay, yeah. So,
Probably I have no working years, but it's not working. Tell me. Well, you know the question right now.
So my question is,
nice.
Hi. When you're on kube control trace, you target a node, right? Well, is it also possible to filter for specific containers or for specific pods, for example?
Yeah, I did that in the demo.
Oh, yeah.
Yeah, sorry.
Now we have
Maybe it
microphone.
wasn't clear. I can show you that.
Yeah.
So the question was, it's possible to target a specific pod with QCTR trace? Yes, it is. Like in this case here, I was using pod/, name of the pod instead of what is happening,
No.
instead of the node. It turns out that this support is not very well done yet because we have to do some changes to BPF trace to support PID namespaces. It kind of works, but there are works to make it better. And there's actually support for C-group V2 in BPF trace that you can use with QCTL trace, but C-group V2 are not the default in Kubernetes. So I didn't make an example just because it's not. Alban there is doing a talk this afternoon that shows the C-group support very well.
So yeah, we found a microphone.
Nice.
Do you hear me? I don't hear myself that well. Anyway, any other question? Oh, yeah.
Please be kind.
Hi, thank you for the presentation, really nice. I'm really interested in this, but I'm also scared. Is there any chance I can shoot myself in the foot? I want to test this on a server and then I do something stupid, I run out of bandwidth, out of CPU or something, and I cannot connect to the box anymore. Is it possible for me to...
It is possible with BPF in general. Like, for example, well, the only use case that happened to me that I basically locked out myself of the machine has been with XDP because I was managing with packets, so I just basically dropped all the packets and my SSH packets too. Like the same things you do with IP tables. And that happens, or like that you create a loop with packets continue going to the same interface and you basically lock yourself out. But BPF programs are not persistent in that way. You have to load them again. So you just restart the machine. And with BPF trace, it doesn't allow you to do this kind of thing. So not with BPF trace, but with BPF in general. Yes.
Next question. Oh, we have two.
Thanks for a great presentation. I think very, very useful tools for my mostly Kubernetes administrator, so I will use some of your tips. But my question is, have you used SysDic, and could you compare this solution with SysDic?
Well, yes, I use SysDic too. SysDic runs as a kernel module. And that's one of the things I want to avoid personally. My machine likes to run kernel modules for monitoring. So I was starting exploring this thing. I think that SysDic does very well the presentation of the data they extract. But I think that those data can be extracted also within the eBPF program. So like, it would be cool if there was an eBPF tool that extracts the same information as SysDic. This microphone is driving me crazy, and but that has a nice interface. That's what we mean. Like that's the same reason I did this, because I just wanted to have something that just let me do stuff like without having to SSH in all my machines and run the programs. Also because I don't really know where the things are running with Kubernetes. So yes, I like the SysDic.
Sorry for the microphone interference.
Thanks
We
for
have a
the
question over here.
Thank you for the presentation. SecComp is still using classic BPF, not eBPF.
Yeah, it is.
Do you know if and when the eBPF support will be extended to SecComp?
It's a tough question. I've been reading recently on the LKML that it's arriving. I don't think it's coming this year. So honestly, I don't think that's any progress. That's like measurable in a way that you can say, hey, in June it's arriving. But that's all I know. I'm not involved in that. So.
Any further question? Okay.
Thanks for the question. And thanks for qualifying that's classic BPF.
So can you aggregate data from around the cluster, or do you need to target a specific node or a specific container?
Nice question. And not yet, because BPF traces with kubectl trace, right? You're asking, or in general? With kubectl trace, not yet, because BPF trace has been created specifically for single nodes, so you cannot. But it can be done. Well, we are working on that. Like we are working on like having BPF trace expose a different format to aggregate from multiple nodes, but not yet. But that's in my personal plans at least, because I'm probably doing that. If anyone wants to contribute that, I will be super happy. But it's mostly in BPF trace because kubectl trace just runs that. I can run the program in multiple machines, so it will work right now with streams, but it doesn't work with aggregation because aggregations are basically done in that machine directly. Thanks for the question.
Hi, thanks
Hello.
for a nice presentation. More of a general BPF, eBPF question, but also maybe can be applied to Kubernetes as well. How safe is it to run a tracing a program on a high-load production server to do real analysis of what's happening? Is it going to affect performance? And if yes, is there any numbers of what you can expect? Of course, it's really probably difficult to answer depending on what the program's doing, but
yes.
Yeah, the question is how safe is it, and can you actually run this in production to see how it works?
Thanks for the question. It's a thing that I missed saying in the talk, so thanks for the question. What you usually do to know what your program are doing in general is like you use a debugger or use strace, these kind of tools. Those tools actually put interrupts or dwarf symbols or whatever in your program, so they need to interact with your program in a way, while BPF doesn't. BPF goes to the kernel receives all the information from the program already, and you just attach yourself on a side and get the information the kernel already has. So the performance impact is not, it's always not in the program itself, it's more in the kernel because the kernel needs to process your code, but it's very low. Like you will never, well, you can do that, but you will never attach like strace in PID1, right? While you can do that safely with an eBPF program. Okay. Thanks for the question. That was a thing I missed to say.
We have another question over here. Any other question?
Some questions.
Okay. Then thanks for the talk.
Thank you.